Hello and welcome to this episode of Math with Martinez. We are in our pre-calculus unit 10 where we are looking at vectors. And throughout this video, we're going to be focusing on linear combinations and trig forms. So let's get started. The standard unit vectors, I and j, are positioned like you see here along the x and y axes. And that I vector, that horizontal vector, is going to be defined as, in component form, 1, 0. And j, that vertical component, that vertical vector, is going to have components 0, 1. Which makes sense. These kind of are corresponding, if you're thinking about your unit circle, with those quadrant angles. And so we're looking at those special little unit vectors. Now, why would we have unit vectors? Well, we can actually go ahead and take vectors and think about writing it in this form that we're going to see, and it is to write it as AI plus BJ. And that is called a linear combination of our vectors I and j. Now, a and b are these components that are multiplying with our unit vectors I and j. And so what I want to show you guys is the proof of why the vector in component form AB can be written as, in linear combination form, AI plus BJ. So here's what we're going to want to do. In order to prove this, what we'd start with is rewriting it as the sum of two vectors. So instead of just vector AB, what we're going to write it as is the vector where A is adding, where we have the sum of two vectors. So our vector V is equal to the vector with components A and 0, and added to that, the components for the vector, the second vector, to be 0 and B. Now, what we can do is factor out from each of those separate vectors written in component form their A's and B's, so that they are a scalar. So this could be thought of as A times 1, 0, the vector 1, 0, and B times B as a scalar multiple for the vector 0, 1. And what is the vector that we have right here that I'm highlighting in green? That is your unit vector I. So we have that it is A times vector I, and adding to that, what do we have? B times, well, again, focus here on this right here. What is that vector? That is the definition of our unit vector J. So that's just the proof of why we can go ahead and write this vector as in a linear combination format. So what we're going to do here is rewrite each vector as a linear combination of I and j, of our standard unit vectors I and j. So vector v here in this first example would be rewritten as 2 times that standard unit vector I, added to that 5 times the standard unit vector j, where the I is, again, this horizontal unit vector, and j is this vertical unit vector. So when you're looking here at your A and B, remember that A corresponds with that horizontal, that's the horizontal component, and B is the vertical component. So n, how would we write this? It would be to write it as negative 7I plus 3 times the unit vector j. So that's pretty straightforward when your vector is already in component form. What if instead we have a vector like we do in 3 and 4 where they are giving us the initial and terminal points? Well, what we'll want to do is go ahead and rewrite vector rs. First, we'll do it in component form. So let's label this x1, y1, x2, y2. And so that is to take your x values, which is negative 5, and subtract from that the negative 9. And the difference of your y's, negative 6 minus 8. What's that going to be? That's really adding. So this is 4, negative 14. And I need just a little bit more space. Now with it written in component form, we can go ahead and write it in the linear combination of I and j. That would be to write it as 4I minus 14j. There you go. And lastly, why don't you try example number 4? Begin by writing the vector PQ in component form, and then write it in the linear combination, as a linear combination of I and j. Would you guys take a moment? Try that now. All right, well, when you were writing it in component form, that would be to take the difference of the two coordinates, making sure that you take negative 2 minus negative 10 and 5 minus 6. That is actually the sum, so it's going to be 8 and negative 1. And so when you take that and write it as a linear combination of I and j, it would be 8 times that standard unit vector I, and subtract from that 1j, which we can just write as minus the standard unit vector j. All right, so there you have it, ladies and gentlemen. That is writing linear combinations of I and j, those standard unit vectors. And what I want to show you all here is now trigonometric forms of a unit vector, right? So kind of connecting what we've been studying throughout this year. If u is a unit vector, then the terminal point of u lies on the unit circle. Remember, your unit circle has a radius of 1, and so if we are just 1 unit away from your origin, well, that's where the standard unit vector I and where the standard unit vector j would be terminating on those quadrant angles. So u could be rewritten as, that unit vector u could be rewritten as the x and y, but remember in your unit circle, x is the cosine and sine of theta is the y value, the horizontal and vertical. So our standard unit vector u could be rewritten, our vector u could be rewritten as cosine theta, sine theta. And if we were to instead write that as a linear combination, it would be that vector u is written as cosine theta times I, and add to that sine theta times j. Now, because every vector v is the product of its magnitude and its corresponding unit vector, we can actually write v in the following form. Remember, your vector v is actually going to be the product of its magnitude and its corresponding unit vector. So again, how would that be? We've got the magnitude of v multiplying with the unit vector. And what is our unit vector? Cosine theta, sine theta. That's the first part of it. And to write it in component form, or to go ahead and multiply this scalar into it, that is to take the magnitude of v, multiply it with cosine theta, magnitude of v, multiply it with sine theta. Or in linear combination, the magnitude of v times the magnitude of v times cosine theta, unit vector I, and magnitude of v sine theta, standard unit vector j. You're going to want to stay tuned, because now with these definitions and our ability to write trig forms of a unit vector or a vector in as a linear combination, we'll be able to answer a lot of really cool application problems dealing with bearings and direction and all kinds of stuff like that. So yeah, right now it feels kind of vague and abstract, but we're going to see applications and recognize why this is actually truly beneficial in solving real world problems. So until next time, stay fired up, you guys.